G'day, in this video we're going to be focusing on the particle wave nature of matter. This concept is included in dot point 8.3.4, and we're still looking at deepening our understanding of matter and the electron. In particular, we're looking at de Broglie's work in describing matter as a wave, as well as some of the experiments that shortly followed that proved this concept. So today we'll first outline de Broglie's ideas on particle wave duality, and explore how de Broglie was able to quantitatively account for this duality, then unpack the experiments that were conducted, which in turn validated de Broglie's ideas and work, and we'll talk about his contributions and limitations at the end as always. From a historical context, at the time of de Broglie and his beginnings of his PhD thesis, Einstein had already introduced the concept of wave-particle duality for light, and this was through the introduction of quantum concepts as well as evidence from experiments involving the photoelectric effect. In de Broglie's PhD thesis, he wanted to explore wave-particle duality for matter. And going into this work, he was hopeful that his findings would help to explain Bohr's postulates, particularly the ones surrounding the behavior and nature of electrons, and how these electrons don't emit radiation as they orbit, and thus exist in stationary states. The centerpiece of de Broglie's work is his namesake, the de Broglie equation, which is in your datasheet. It says that lambda is equal to h on mv, where lambda is the wavelength of our matter wave, h is the Planck constant, the mass of the matter with wave-like properties, and v is its velocity. This in essence was actually just a combination of two very famous and very important equations in this space created by Einstein and Planck, E equals mc squared and E equals hf. If we assume that matter has wave-like properties, we can equate these two formula. Note here as well that I'm going to be replacing v for c because these matter waves may not be for particles which are traveling at the speed of light. We can simplify this equation further because we know that v is equal to f lambda for any wave, and therefore f is equal to v on lambda. From here we can write an equation which solves for lambda. Now, while this equation does not account for relativistic speeds, later work in this field did reveal that de Broglie's formula was conceptually consistent in these scenarios as well. What this formula suggests is that for matter which has both mass and velocity, there can be an associated wavelength which describes its wave-like properties. This was quite effective in addressing some of the flaws in the Bohr model of the atom. This then provided a reasonable explanation for why electrons existed in stationary states where they were not emitting radiation. Essentially, instead of the electrons accelerating in a circular orbit, they instead formed a circular standing wave. And as such, we would see these standing waves have very specific geometries and characteristics. Each of these possible standing waves corresponded with each of the orbitals which existed in the atom. You'll note here that as we increase our orbital number, our n value, the number of nodes and antinodes increase in the standing wave, respectively. The key idea here being that the circumference of the wave had to be equal to a multiple of the wavelength of the standing wave. In other words, to form a standing wave, you couldn't form a circular standing wave with a circumference that included one full wave plus 0.6 of a wave. As a result, you could only form standing waves at specific radii, linking with Bohr's concept of discrete quantized energy levels. This also connected quite well with Bohr's postulate that the angular momentum of an electron in an atom is quantized as well. This effectively was another way that Bohr was able to express the idea that electrons could only exist in discrete quantized orbitals or energy levels. As such, the angular momentum for these electrons were also discrete and quantized as well. This can be described in a couple of ways. The angular momentum L can be expressed as mvr, but it can also be expressed as nh on 2 pi, where n is the orbital number, h is a Planck's constant, and 2 pi is there in the formula to account for the circular shape of the orbital. It's not something that you actually have to process and calculate with, and it's not a direct part of our syllabus, but I am going to use it as a way to demonstrate how the de Broglie concept and the de Broglie equation was able to again explain elements of Bohr's model, which he did not have a complete answer for himself. So we're already getting familiar with the de Broglie equation that lambda is equal to h on mv, but there's also another equation that we can use based on de Broglie's conceptual understanding of electrons and their orbitals, and that is that n lambda is equal to 2 pi r. Essentially, what we're saying here is that the circumference of any orbital is equal to the wavelength of the standing wave multiplied by the integer of the orbital that we are analyzing. N equals 1, n equals 2, n equals 3, etc. From here, we can substitute our de Broglie equation into our second equation, and what we'll find is that once we rearrange this formula, we will have a statement that supports Bohr's postulate about the quantization of angular momentum for these electrons. Again, these mathematical relationships continue to support the idea of de Broglie's equation and its validity. This really made scientists of the day start to seriously reconsider their understanding of matter. The mathematics held true, but was dependent on de Broglie's assumption that matter had this wave-particle duality. And it was this element which was yet to be proven. If it could, then de Broglie was on to something truly new and spectacular. A few years later, Davison and Germer were working on trying to demonstrate the wave-particle duality of electrons. They did so by firing a beam of electrons at a nickel crystal to image its structure. Effectively, they were trying to replicate experiments involving a field of science called crystallography. Now, crystallography was usually conducted using X-rays, and was based on the idea that incoming X-rays would diffract as they passed through the gaps between atoms in a crystal. Effectively, we would be seeing behaviors that are similar to what we see in Young's double slit experiment. You can see here when we're looking at things about the path length difference, for example, we are using our d sine theta is equal to n lambda formula that we see and use in our other diffraction experiments that we did in module 7. Using de Broglie's equation and assuming that they were able to fire their electrons at a suitable velocity, the calculated matter wave in this scenario provided a wavelength of 1.67 angstrom. Note that the angstrom is equal to 10 to the negative 10 meters. Matter waves of this wavelength are comparable to X-rays, and therefore electrons should, in theory, if they do have wave-like behavior, should be able to be used in this experiment in exactly the same way that X-rays are. Turns out this hypothesis was correct, and they were able to measure electron scattering where there was a peak intensity of scattering at 50 degrees, lining up quite closely with their predicted behavior. Similar experiments were conducted shortly afterwards as well. George Thomson also substituted electron beams for X-rays in similar experiments. In this experiment, he passed X-rays and electrons separately through metal foils. This experiment had already been done with X-rays in the past, and for aluminium, we would see a diffraction pattern that looks something like this. The lower half, however, is a diffraction pattern which is caused by electrons passing through a thin sheet of aluminium. Quite obvious to see there is a very large degree of similarity between the two resulting images. As these images are caused by diffraction, and diffraction is a property of waves, it is again experimentally suggesting that matter, under the right circumstances, can demonstrate wave-like properties and behaviors. One more example for you of experimental evidence. You can actually also conduct Young's double slit experiment, which we've done and looked at multiple times already throughout this course, with electrons as well. Not just with waves, but also matter. Original hypotheses would have predicted a result like this, firing the electrons through two slits and ending up with two bands of intensity on the detector screen at the end. This is based on the idea that the electrons will pass through the slits and continue to travel in relatively straight lines. But when we actually did it, we see an interference pattern consistent for what we would see for electromagnetic waves. And by accounting for the voltage in the electron beam gun and therefore accounting for the velocity of the electrons, we can use a de Broglie equation to predict the wavelength of this electron wave or this matter wave. And therefore, using our diffraction formula that d sine theta is equal to n lambda, we can confirm that the theoretical distance between our areas of constructive interference match with the experimental evidence. which they do. So this begs the question, if matter can behave like a wave, why don't we see this in everyday life? Why was it first observed through very specific experiments looking at the behavior of electrons? Put simply, this is an issue of scale, and I would like to show you a scenario to demonstrate what I mean. If we were to calculate the de Broglie wavelength of a 1 kilo block traveling at a meter per second, all we would need to do is to substitute m, v, and the Planck constant into our de Broglie equation. Now, conveniently, this just equals the Planck constant, which is 6.626 times 10 to the negative 34, but the units aren't the same because the units here are in meters. We're getting a wavelength. This means that the de Broglie wavelength for a macro scale object is ridiculously small. As such, if we want to observe the wave-like nature of this matter, we would only be able to do so at significantly small scales. Remembering before, when we were talking about gaps in a nickel crystal, these gaps were equal to 2.15 angstrom, which is 2.15 times 10 to the negative 10 meters. This distance here is exceptionally smaller, incomprehensibly smaller than this gap between two nickel atoms in a crystal structure. As such, observing this kind of wavelength in any meaningful way is near impossible, and certainly is not observable at our regular everyday macro scale. As such, it's no surprise that we find it completely bizarre that matter would behave in such a way like a wave. Yet our experimental evidence concludes beyond all doubt that it can and does, and is particularly pertinent when exploring physics at the atomic and subatomic levels. So to conclude, de Broglie's work was a huge jump in our understanding of the atom through applying quantum mechanics. The biggest advantage being here that we were slowly but surely moving away from any explanation for the behavior and properties of atoms and subatomic particles that were based around classical physics. However, there were definitely some flaws. De Broglie was not able to, in his work, articulate what the wave actually was. He was just able to demonstrate that the mathematics worked and that this was an inherent property of the electron. Furthermore, his model also ignored any kind of relativistic correction, which are obviously necessary if we are going to look at the behavior of any type of matter that is moving at a speed approaching the speed of light. In order to do that, there needs to be some significant overhauls to the simplistic nature of de Broglie's equation. Next time, we're going to be looking at the Schrödinger equation, which is significantly more complex. And while we're not going to be digging deep into the mathematics of the equation, we'll be very much focused on how this equation took our understanding of the electron and its behavior in the atom even further. But until then, have a good one.